So today we're going to continue with our sort of talking about permafrost. And it may seem like a funny idea for those of us down here quite a long way from the poles. But a lot of the land and a lot of the soil around the northern hemisphere, especially close to the Arctic, is frozen. It never thaws out, even in the summer. Even if the very top thaws out, we don't get the melting further down. And you say, well, why should this bother me? There's sort of lots and lots of thousands of square miles of this stuff. But really, why should I care about it? And the reason that you should care about it is because of the carbon cycle. Because of those same reasons that we care about the fact that we are putting CO2 into the atmosphere. Because methane and soil contains a lot of methane. Soil itself contains a lot of methane and carbon dioxide. And the fact that it's frozen right now means that it's trapped. And so obviously, if we're going to thaw that out, we need to know how much of that is going to happen. So today we're really going to talk about permafrost, how we monitor it, what changes we're observing, and what are the implications of those changes, both to people but also to the wider Earth system. So as a quick reminder, quiz 4, I think it's a slightly easier quiz this week. I tried to take pity on you guys, so hopefully it's not too painful. And so here's a quick reminder of what we talked about on Wednesday, the fact that we have this active layer. And the reason that we call it the active layer is because there are active biological processes going on in that particular layer. Not so much in the winter when it is frozen solid, but definitely in the summer when it thaws out and it rises above 0 degrees Celsius. But that sun's energy doesn't heat all of the soil instantly. It takes a while to heat the surface and then for that energy to sort of conduct downwards. And so by the time we get to a certain depth, it still stays frozen throughout the year. And that sort of chunk of soil that stays frozen is called permafrost. So soil that's frozen for more than 1 year. And then both within, like little pockets within that permafrost and also underneath, we have what we call talc, which is basically thawed out permafrost. It's permafrost which is now above 0 degrees Celsius again, so it's just regular soil as far as we're concerned. Okay? And we looked at our lovely trumpet diagrams that everyone liked so much, and we said that these are hugely helpful for us to imagine what's happening in terms of what the soil temperature is doing. And do you remember we said that, say our average temperature is somewhere below freezing, if we look at what temperature does in the soil, then it actually gets warmer with depth because of our geothermal gradient, the fact that the center of the Earth is hot and heat is very, very, very slowly and gradually escaping out to space. And this is very much exaggerated. It sort of takes a long time to get warmer as you go down. It's only a very slight gradient, but it does happen. But near the surface, we need to take into account that our temperature profile also is altered by the maximum summer temperatures, in which case it sort of bends up. And the point where our summer temperature profile crosses our freezing point, our 32 degrees Fahrenheit, or 0 degrees Celsius, if you're more scientific, that's sort of the depth of the active layer. And underneath that, that's going to be permafrost. Even in the summer, it doesn't get above 0 degrees Celsius. And obviously, the winter temperature, we don't really care that much because we know it's cold enough in winter for that soil to be frozen, and it's frozen all the way to the top. Okay? So it's really that summer that we care about the most. So here is my little geothermal gradient. I've got my summer and winter profiles, and that dotted line there shows sort of where the average annual temperature would be. So my question for you is, what would the depth of the base of the permafrost be? So not the top, not where the active layer meets the permafrost, the base of the permafrost. At what depth on my graph would that be? Okay, has everyone had a chance to vote? Okay, let's take a look and see whether we remember what we did on Wednesday. So at least 68% of us remember what we did on Wednesday, because D is the correct answer, okay? And I enjoyed seeing everyone do this sort of this in the air when I was asking this. And the way you tell this is you look, basically, if you draw a line down at 0 degrees Celsius, which is our freezing point, on this side of that line, you're going to be warmer, and on this side, you're going to be colder. And so if we look at, say, where our geothermal gradient crosses that 0 degrees Celsius line, underneath 30 meters or so, it's warmer than 0 degrees Celsius, so it's not going to be permafrost. But above that 30 meters depth, then we will be permafrost because the soil temperature is below 0 degrees Celsius. Does that make sense now? Yes? Well, you'll have a chance to show it in the quiz as well, so hopefully you get that. Okay. So what are some of the problems we have when measuring the change in our permafrost? Can you think of any problems with actually monitoring how our permafrost is changing? Is it easy to monitor permafrost? No, why might it be difficult? It's underground, absolutely. So one very good reason is it's underground, and so it's pretty inaccessible. It's something that even if we're sort of monitoring snow cover with satellites or sea ice with satellites, it's much more difficult to get at, say, ground temperature. And even if we can get the very top of the ground temperature, we can't necessarily say what's happening deeper down. And so it's actually pretty difficult to monitor permafrost, and especially where we have extremely thick permafrost. If, say, it's a kilometre thickness, it is much more difficult to sort of measure and see what's happening. And so it's actually a lot more time-consuming to really monitor what's going on in permafrost, because you need to dig a big hole, basically. And there are a certain number of spots, and they're shown in little, sort of, you can see like M&M type colours on the map there. And you can see that, well, there's a cluster in Alaska, there's a cluster around, say, northern Europe, and then there's sort of a cluster around maybe the northern coast of Russia. But there are enormous areas where there are no boreholes at all. And so we have these little measurements, but they are a little bit patchy. And if you imagine all of those different things that we said affected permafrost, things like the type of soil, how much moisture there is in the soil, what the vegetation cover is, even things like sort of what your soil thickness is, all of these things will affect your permafrost and how it responds. And so it's really difficult for us to say for an enormous area exactly how our permafrost is changing. And it's expensive to do this and to keep those instruments there and working. Okay, so it's actually something that's pretty difficult to monitor and very time-consuming. And it does respond relatively quickly as well. Okay, so these things are a bit challenging to measure. And so I'm going to give my voice a little bit of a rest and you a chance to hear someone other than an English person. And I'm going to play you a very, very short little video, sort of 4 minutes or so, but it is a really nice introduction, I think, to the rest of the lecture today. So here we go.
Frozen ground is so cold, it stays frozen even during the summer.
Permafrost is any earth material under ground surface which at or below 0 degrees Celsius for 2 or more consecutive years.
Approximately 50% of the Soviet Union is on permafrost, ground that never thaws completely.
Some permafrost has been frozen solid for thousands of years, but not anymore. Because of a warming climate, permafrost is warming too, challenging the people who build on it and live on it, and accelerating global warming even more. Permafrost makes up nearly a quarter of all the land in the northern hemisphere, about 8.8 million square miles. In some places like Siberia, the ground is frozen 1,000 feet deep or more. In interior Alaska, the permafrost dates back to the last glacial cycle.
We're close to 30,000 years old here.
10 miles north of Fairbanks, the U.S. Army Corps of Engineers Cold Regions Research and Engineering Lab operates a tunnel where scientists can research permafrost, its geological properties, and the fossils frozen in its walls. Dr. Matthew Stern is their chief scientist in Alaska.
The Permafrost tunnel was built in the 1960s. The reasons at the time were to see how you dig permafrost. Over time, the tunnel, I like to think of it as a phoenix. It keeps rejuvenating itself. There's other new questions we can investigate. So modern questions now have to do with climate change, changes in environmental systems. But we're also interested in how to deal with permafrost because it's still a big issue in Alaska.
Alaskans have known for years all about the shifting nature of permafrost. Large parts of the Trans-Alaska Pipeline had to be built above ground on stilts to prevent the permafrost below from thawing. And Fairbanks, Alaska's second largest city, is dotted with pockets of permafrost. The sinkholes, collapsed roads, and tipping houses are clues to places where it is warm. But now measurements around Fairbanks show that in many places, permafrost temperatures have risen so much that it is only 1 degree below freezing. At the University of Alaska's main campus, geophysics professor Vladimir Romanovsky runs the Permafrost Laboratory. He uses a Russian word to describe thawing permafrost, talik.
And talik, it means not frozen in Russian, just simply not frozen. It's very important now because these taliks start to develop because of warming in climate. And the development and growing of taliks is really an indication of permafrost degradation.
Romanovsky has planted 45 boreholes deep in the permafrost all over Alaska. The results show that permafrost temperatures have warmed as much as 2 degrees Celsius in the last 20 to 30 years. Normally, because of the heat emanating from the center of the Earth, permafrost should be warm at the bottom and get colder as it reaches the surface. But exactly the opposite is happening. Romanovsky's data shows that since the mid-1980s, the temperatures in permafrost have gotten warmer as they creep towards the surface.
And this warming is 100% effect of changing climate, warming in air temperature.
Thawing permafrost can take a toll on buildings and even force entire communities to relocate. But an even bigger cause for concern is the powerful greenhouse gas that gets released from thawing permafrost. Katie Walter Anthony was a young assistant professor.
Okay, we'll come back to her in a little while. So hopefully you were surprised at how many of those terms that you recognized just from Wednesday. And those sort of showed you some of the pictures that you would see if you were based up in Alaska, that you'd see these potholes, you'd see these houses being affected by this warming. So we're going to take a look in a little bit more detail at his particular data. So this guy's data, and this was on his computer in front of him. And it shows sort of what that temperature does. And so we had this sort of nice trumpet diagram where we had our nice geothermal gradient where we said if we had our average annual temperature, then it got gradually warmer as we went down into the earth. And that makes a certain amount of sense. But remember that it takes a really long time for conduction to happen, for heat to transfer within a solid. And so what we're seeing is that if you measure in the same place, so these lines just represent different years, but measuring the temperature in the same place, instead of having that nice geothermal gradient where it gets hotter as you get down towards the center of the Earth, we've seen so much warming of our climate that actually now it's hotter at the surface, and it actually gets colder as you get deeper. And eventually, that geothermal gradient will sort of adjust back to that new annual average temperature, but it takes a while to do that. And so in the meantime, we have this really weird pattern in a lot of places where it's not our traditional sort of view of permafrost, where we have this increasing temperature with depth. So I think that's sort of a really powerful indication that not just sort of the top, but also look, it's down to say 50 meters. We can measure changes in the temperature of the soil that are resulting from just sort of 30, 40 years of warmer temperatures. I think that's pretty astounding. And we can also look at, say, a transect. So we'll look at a number of different boreholes as we go from the south of Alaska to the north of Alaska. And I don't know who drew this graph, but I disagree with how they did it, because in reality, the pale blue line there represents a site further south, and the black site there represents the one furthest north, which makes no sense, right? So if you imagine that sort of those sites are sort of from north to south there, okay? And so what you can see is that in terms of the warming, down at the very southernmost site, we're still pretty close to 0 degrees Celsius, but there's been maybe a little bit of warming, but it's not that dramatic. Whereas if we look at, say, our northernmost site, we've seen a really dramatic increase in the temperature through time. So say from 1970 to 2010, we've seen a really dramatic rise in that temperature. And the key thing to remember is that even though we've seen a dramatic rise there, it's still at -8 degrees Celsius. It's still really cold. So we're still going to have large thicknesses of permafrost, but we can see that sort of 2 degrees Celsius or so of warming within the soil at that particular site. So you can see that the general pattern is that the further north you go, the more of a temperature change you're observing. And that fits with our idea that it's the poles that are going to warm the most as climate change continues. Okay? Remember, the equators, the temperature there doesn't really change very much. It's the poles where we're going to see the greatest change in temperature. So we can actually see signs of this stuff. Even if we don't actually sort of stick thermometers in the ground and measure it, we can see signs that something is going on, that something is changing in our landscape as we look at the landscape up there. So for example, we see changes in vegetation. So from more sort of grassy, sort of what we think of as more traditional sort of tundra vegetation, those pretty sort of boring grasses. And now, because our active layer is getting thicker, we can support things like sort of more woody shrubs, something more like what we have in the right-hand side there, okay? And so that is having an effect on how much carbon is being cycled already through the Arctic. And in general, it's a good thing for us. The fact that we have these warmer temperatures, these thicker soils, and more vegetation in the Arctic means that more carbon is being taken in right now. And so it's sort of taking out some of that extra CO2 that we put in the atmosphere by burning fossil fuels. But it's not just that. If you imagine that we had solid frozen soil and now we've thawed it out a bit, we've made it less stable. It's much easier for that soil to move. And so you can see that all the time around here on those really steep slopes. Then people try all the time to sort of keep that soil back, especially if their house is at the top. Because that soil, when it's not frozen, it's relatively easy to move. And so around Alaska, around different parts of those high latitudes, we're seeing more landslides now, for example. Not only that, but we're seeing lots more erosion. So if your soil is frozen, it's pretty resistant to erosion, pretty resistant to being sort of blown apart or moved apart by water. But as that soil sort of thaws out, then it's much more easy to erode it. And that's especially true along the banks of rivers, which is what's happening here. You can see big chunks of soil are just falling into those rivers. And this actually has a really big effect on the amount of soil and particles being carried by that river. And I met a girl from Alaska, and her sort of tiny little village depended on a lot of fish from these rivers. But because of all of this sort of muddy sort of particles now in those rivers, then it's becoming a less sort of nice habitat for their fish. Not only that, but along the edges of our coastline, where we previously had relatively stable coasts, now that we have those waves sort of bashing into that sort of newly thawed out soil, then we're seeing really extremely fast erosion. And so certain villages along the Alaskan coastline and in Canada are really thinking about having to retreat and having to relocate to adapt to this. I mean, it's not just this. We're going to come on to this topic again next week when we talk about sea ice, because it's not just that the soil has thawed out, but for example, if this sea here used to be covered with sea ice, it prevented these big waves and these big storms from sort of bashing into that soil. And so it's both the disappearance of sea ice and that thawed soil that means that there's so much erosion happening. And in some places, it's like the length of a football field in sort of just a few years. And that's really significant. Okay. And then we have subsidence, and my favorite thing to do with permafrost is our drunken forests. I think they're just so fun, and I love the name as well. So you can see my somewhat drunken trees here. And what happens is that when that soil becomes unstable, they end up with a bit of a lean, and then if they keep growing for a while, they'll sort of grow up again towards the sun. And so in a lot of these forests around lakes, and all over the tundra where this permafrost is thawing out, then one of the most obvious signs is all your trees are leaning all over, okay? So not only that, but also you saw some of the images in that little video, the fact that we have big potholes opening up in roads. It's affecting things like airports and rail lines, things like the oil pipeline. Wherever we have this frozen soil and lots of ice within it, when that thaws, a lot of the time it loses its sort of stability and we get subsidence or sinking, and that does affect buildings as well. Okay, and lastly, we're really drying out our landscape. So do you remember we have a number of things going on, and this is why the Earth system is so complex and gets difficult to think about. So definitely in parts of Alaska where we're warming our air temperatures, we might expect more precipitation in the coming decades. But the problem is that as we thaw out our permafrost, then all of our lovely lakes that were sat on that impermeable layer of permafrost underneath, that was that meltwater that was trapped at the surface, now if that permafrost thaws, that water can travel down. It can go into the soil. And so in a lot of cases, you can see sort of the former shoreline of this lake, and it's just sort of sinking, all that water is draining down. And so what we're seeing in a lot of cases is that we're drying out our landscape. And what is a concern to us here in Southern California when we dry out our landscape? What do we not like when it's been a really dry year? Why might you be worried if you had a house up in the mountains? Fires, absolutely, fires. And this is something that's relatively new in the tundra. Until really very recently, we didn't have big wildfires in this sort of vegetation. But in just the last few years, sort of 3, 4, 5 years, we've seen some really big fires. I think there was one in 2007. Do you remember what it was called? No. It was big. It was really big. And in fact, that fire released more carbon into the atmosphere than the whole tundra had taken up in the last 25 years. Okay? So it's not a simple sort of arrangement of just sort of working out how much extra vegetation we grow. We need to think about these things like if we're drying out the landscape, how much more are we going to burn? Okay, and so it's a really interesting idea, and associated with that fire, there was a lot of soot put into the atmosphere, and we saw, say, in that year, one of the ideas is that we might have had more melting of ice because that black surface where that soot particles got deposited on snow and on ice were much, much better at absorbing incoming sunlight, so might melt more. So there's all these complicated relationships going on in this place where we're changing our landscape so much. For people, we care about this because it really changes the pattern of where our water is. So if you're a small village and you depend on sort of different water sources, it's changing where those are, how much is there, and also the quality of them as well. Just like we talked about with those rivers and soil erosion putting particles in, we're also seeing changes in the quality of our water. And so if we just look at Alaska, if we ignore Siberia and enormous amounts of the rest of the world, let's be selfish and look at Alaska. And so this is a figure taken from Chapter 22 of the US Climate Assessment Report. And if you haven't seen this and you're interested, it's a really fascinating document because it basically takes different regions. So it takes our region, the Southwest, and it comes up with sort of 5 things that we're really concerned about. Things like in our region, it's water supplies. In this region, in Alaska, it's thawing permafrost, it's melting glaciers, it's melting sea ice. Okay? And in particular, this little graph shows the soil temperature. So basically, anything in blue is underneath 32 Fahrenheit. It's in American, so it's in Fahrenheit. And so it's below freezing. Anything in yellow and up to red is above freezing in terms of its annual average. So if we want there to be permafrost, we want that to be blue. We need to see that. And you can see that we start off in 2001 to 2010. A large part of the Alaskan sort of annual average soil temperature is below freezing. It's at freezing or below. It's just really that southern edge, and especially around the ocean, where it's above freezing. But if we take the top sort of two diagrams and the bottom two diagrams, the top shows what happens if we emit an awful lot of CO2. If we just keep going as normal and emit CO2 as much as we can, that's what we get at the top. And our lower, slightly more optimistic idea of what the future will be like and how much CO2 we'll produce is at the bottom. And you can see that in either case, by 2091 to 2100, we're losing an awful lot of that permafrost. That soil temperature is rising very rapidly, and it's becoming above 0 degrees Celsius. And really, only the very top, only the very northern part of Alaska still has significant amount of permafrost. And so this is a big, big change for Alaska, both in the landscape and just how we deal with it. So it's worth thinking about. And so I had a question, which is half hidden under the iClicker. So before I give you my options, I want you to speak to your neighbor and see if you can work out how much extra do you think Alaska is going to have to budget for? How much extra do you think they're going to have to pay to deal with infrastructure damage due to thawing permafrost? So think about it. Come up with a random number. Okay, does anyone have a suggestion for me? Does anyone want to give me a number? $1 million? Higher?
1 billion.
1 billion at front here. Any other bids? 10 billion? Okay, so see if your number fits anywhere into my selection. So there's quite a difference there. So vote for your option. And this is just in the next 20 years, by the way. This isn't up to 2100. This is just the next 20 years. Okay. Have you had a chance to put your vote in? Okay, let's see. So the vast majority of people think C. And there are some much more optimistic people and some more pessimistic people. The answer is D. Okay, so if we look at, say, the Alaskan budget, and so it was a really unfair question because it'd be much more helpful if I told you how much they usually spend. They spend maybe about $50 billion every few years on sort of infrastructure, things like roads, water supplies, airports, rail lines, all of those sorts of things. So what they're looking at is sort of another 10, perhaps even 20% as we go forward in time on top of that normal bill. And so that's a pretty substantial amount of money. We're not talking about little sort of a few million here or there. This is a really big deal for them, and they need to sort of be building this in because this is just the next 20 years. So it's pretty substantial, these changes. Okay. So that was just Alaska. So let's look at what's sort of happening in a broader picture around the northern hemisphere as we go forward. So today, we probably, and look at the word probably because remember it's really difficult to measure. We probably have about 10% less permafrost than we had sort of 100 years ago. Because of the warming that we've already seen, we probably have about 10% less. And as we continue to warm our climate, and depending on how much we warm our climate, depending on how much CO2 and other things we emit, then we will continue to see permafrost loss. It's not a stunning revelation, I'm sure. And so what this little graph shows you is for just one of those scenarios, where and how much change we're going to see. So the black there, those little black sort of squares, represent a complete loss, a complete thawing of our permafrost. And then you can see that the rest here shows the active layer thickness. And so you can see that, again, we get our thicker active layer just sort of on the edges of that as we sort of deepen our permafrost and melt it from the base as well. Okay? And so we are looking at substantial changes, not just in Alaska, but also through northern Canada and around Siberia and northern Russia as well. Okay. And that's just one little map to give you an idea. I wanted to give you an idea of our uncertainties, because it is a giant mess, basically. So, of course, we're going to expect more thawing of permafrost if we warm, but how much we're going to see is really much more of an interesting question, okay? And so this little table here gives you a number of different studies, and I know that you're all very young, but look at the dates of these. So 2005, 2011, 2008, these are all really recent studies. This is something that we're really actively researching because we don't have that good an idea and we need to know what is going to happen. And then for each of these studies, this is the % decrease in permafrost area that they estimate might happen. And this is the increase in the active layer thickness in centimeters. Okay? And so I blew up the table there. So it's not an likely question, but I want you to look down that and find me the minimum change in permafrost area and the maximum change in permafrost area. So what is the range of our uncertainty here? So what's our minimum estimate? 7%. So that's pretty good news, right? We could only lose 7% of our permafrost area. What's our maximum estimate? 90%. So that's really helpful, right? We could lose anywhere from 7 to 90% of our permafrost area. So this is why it's an area that we're really interested in researching, but it is expensive and it is difficult to do. So this is sort of why we need to put more effort into this. Okay. So why is it important? Why should we really care whether it's 7 or 90% if we don't live in Alaska? And it's because of our carbon cycle. So hopefully this is vaguely familiar from high school, but as a quick reminder, if you haven't seen it for a while, we have CO2, carbon in our atmosphere. That carbon can leave the atmosphere by going into vegetation, by going directly into soils sometimes, by being dissolved in the surface ocean and being used by life in the surface ocean. And then it sort of gets circulated between all of these different things, between the air, between vegetation, between soils, between our ocean, both the surface and also the deep. And a lot of our carbon is in the oceans. But also we have quite substantial amounts of carbon in our soils and in our vegetation too. And so our question is, if we're going to thaw out significant volumes of soil, what is that going to do to where that carbon is? Okay, what's that going to do to the amount of carbon in our atmosphere and so the amount of warming we might see? And so here's a lovely little diagram. I forgot to put where it's from. I think it's from one of the newspapers from the UK, that shows you really how that permafrost builds up. So if you see it, if we start at the top diagram, we have ancient grass and shrubs growing quite happily in our pretty cold tundra environment. And then we have that active layer, that seasonally frozen layer of soil underneath, and then the continuously frozen ground below. But what happens is that as that plant material dies and sort of gets incorporated into the soil, if we add material, if we're sort of depositing sediment onto that sort of soil surface, if we're just sort of building up the amount of organic matter, then every now and again, as that sort of permafrost layer thickens, we end up with more and more organic matter as we build up our permafrost thickness. Okay? And the problem is that when that temperature then increases again and our permafrost starts to melt out, we still have that organic matter. Because basically permafrost acts a bit like a freezer. You put your food in there, and sort of 3 months later, 9 months later, you come back and hopefully it's still good, right? Because it's underneath that freezing point, and so bacteria and things don't have a chance to attack it and use it and sort of undergo decay, okay? And so all of that nice organic matter that's stored in our freezer, in our permafrost right now, as we warm that up, as we basically sort of accidentally switch off our freezer, then that is starting to thaw out. And so now all of that organic matter that was locked away can be attacked by microbes. And you can see that here they show that sort of drunken forest as that permafrost thaws out. But also you can see that we have these sort of bubbles coming up from the thawing material underneath lakes. And I want to show you the rest of that little video that we didn't quite get to, because these little bubbles that come up from under lakes are really what we're concerned about and what we're interested in. So here is Katie from UAF to tell us more.
On a frozen lake in interior Alaska, outside of the University of Alaska Fairbanks campus. And this ice is already about 20 centimeters thick. So as it's been freezing up, methane gas has been coming out of the bottom of the lake and getting trapped in the lake ice. If you look at the shore, you can see that there are lots of trees that are falling in the lake and they're dying. What's happening is the permafrost is thawing. The ice that was in the ground, when it melts, causes the ground surface to collapse. When the forest falls in and any organic matter, dead plant and animal remains that were in the permafrost, thaw out in the bottom of the lake, microbes decompose it, and it generates methane. And methane doesn't like to stay in water, in solution. It forms bubbles, and those bubbles make their way to the surface. In the summertime, the bubbles pop and they enter the atmosphere. In the winter, however, this ice forms a cover on the surface of the lake. And the bubbles get trapped right under the ice, and the ice thickens and freezes around them. So what we have out here is like a time-lapse photograph of methane emissions from the lakes. Methane is a very potent greenhouse gas. A molecule of methane is 25 times stronger than carbon dioxide. Methane is formed in millions of lakes around the Arctic where permafrost is thawing. And each year, these lakes are emitting already tremendous amounts of methane. But when we look at how much carbon is in permafrost still frozen, and the potential for that permafrost to thaw in the future, we estimate that more than 10 times the amount of methane that's right now in the atmosphere will come out of these lakes.
So there you go. There's so much methane coming out of these lakes, you can set fire to it, which is a lot of fun and looks somewhat lethal. But this is the problem. And so she's doing really interesting things where she's looking at how much of this methane is coming out of these lakes. And why are we getting methane rather than CO2? So here is just a beautiful picture that a student sent me last year, and I loved it so much I wanted to share it with you guys again, showing one of these frozen lakes, and you can see the different generations of sort of bubbles and sort of methane that have been generated as that ice has thickened over the winter. It's really beautiful. So, here is my little baby mammoth, who unfortunately is no more. But why do we find every now and again things like this in our permafrost? So why is this little baby mammoth so well preserved? Okay, I think that's more or less everyone. Right. Yes, obvious answer of the day. I've already said it so many times. It's too cold, okay? And in particular, it's too cold for microbes to attack it and use it to decay, okay? And so our question is, why do we get, say, CO2, carbon dioxide, versus methane? So does anyone have any ideas why we might be getting methane bubbling up under lakes and why we might be getting maybe CO2 released from soils? Clues in the name of the compound. What do you think? So they both have carbon. What does one of them have? Oxygen, absolutely. So it's whether we have oxygen in our environment or not. So normally, we know this, that in soils, especially sort of drier soils, then when we see that process of respiration, which is that basically the opposite of photosynthesis, we see our little reaction like that, the one at the top, where we take really simple sugars, things like CH2O, so the simplest possible sugar, it's maybe glucose, and then we combine it with oxygen, and we produce CO2 and H2O. And that's what we do to produce energy. And it's that process that also microbes are doing in order to produce energy for themselves as well. And that's our decay process in our soil. And that's all very well, as long as we have O2, as long as we have oxygen in our environment. But if we're in really sort of peaty, sort of boggy soils, if we're at the bottom of a lake, we don't necessarily have that oxygen around. And so instead, we have much more complicated reactions going on with different types of little microorganisms. And instead, we get, or as an example of the reactions we see, we have these bottom two going on. And it's not breaking down glucose directly in this case. It's some other organic compound that you don't need to know the name of. But say if we take that CH3COOH, we can sort of have little microorganisms, and that they sort of use that and break it apart in order to obtain energy, and that produces methane, CH4, and CO2. And not only that, but then we have other little organisms that use that CO2 that's produced, and they combine that with hydrogen, and what we end up with is even more methane and water. So these are just some of the more complicated the reactions that can be occurring in our soils, and especially where we don't have oxygen. Because where we have oxygen, that top one is by far the easiest thing to do. It produces the most energy. But where we don't, we're still going to have decay. And so these bottom reactions might be more important. And so definitely, say, in sort of waterlogged soils or in the bottom of lakes, our methane is produced. And both of these are greenhouse gases. But methane is particularly a very strong greenhouse gas. It can absorb 25 times the amount of energy that CO2 can. We don't talk about it as much when we're talking about climate change because there is way more CO2 in our atmosphere. And we are having a much more of an impact on that amount of CO2. Also, methane doesn't last as long in our atmosphere. It tends to become, it sort of oxidizes to become CO2 on sort of 10, 20-year timescales. But while it's up there, it has a really big impact on the amount of warming that we see. And so our concern is that as we melt or as we thaw out more of this permafrost, well, first of all, just how much of that permafrost is going to thaw. Secondly, how much carbon is there in that permafrost? We don't necessarily have good measurements of that. And thirdly, what balance of CO2 and methane are we going to get? Is most of it going to be CO2 and perhaps just a little bit of methane? In that case, we don't need to worry perhaps so much. But if much more of it is going to be methane, then we need to start thinking about that much more carefully. And again, that's something that's really difficult to predict because it depends on very localized conditions, basically whether your decay is happening under a lake or not. So it's much, much more difficult for us to sort of say what's going on. So this is a nice little summary diagram sort of towards the end. So you can see that today we have relatively little vegetation, so we're not having much carbon taking in the Arctic. We're starting to see this second diagram now, where warmer temperatures in a slightly thicker active layer are allowing more vegetation to grow, and so we're actually taking in carbon. We're taking in CO2 from the atmosphere right now. We're a sink from the atmosphere in the Arctic regions. But the concern is, of course, that if we keep on thawing out our permafrost, then even if we're still taking in more CO2, even if we still have lots of vegetation, are we actually going to be matching what comes out of the soil as it thaws? So is the amount in going to match what is coming out, or is there perhaps going to be more coming out than our sort of extra plant growth can account for? And so just to give you some rough numbers, near that surface, so our top 3 meters, so 1 to 3 meters, so where our permafrost is really the most vulnerable to change, It takes hundreds to thousands of years to accumulate this carbon, and it takes maybe tens to hundreds of years to release it. And we've got maybe 1,024 gigatons of carbon in that soil. And if we compare that with all of the carbon in our atmosphere today, we have maybe 780 gigatons in our carbon. So it's a substantial amount. As we go deeper, it takes longer to form and longer to release, but again, there's substantial amounts. And then as we go even deeper, we really don't have a fair idea of what's down there, so we're much more uncertain there. Okay, so that's all for this week. Next week, we're going to move on to sea ice.